Good afternoon, everyone. It's a great honor to present our study, a review of FPGA-driven LLM acceleration on behalf of my authors today. Since the Transformers introduction in 2017, large language models have grown exponentially in size, while single chip capabilities follow Moore's law. LLM parameters outpace hardware scaling. This creates a massive gap where we can train on distributed capacitors. Deploying these models on resource-constrained hardware for inference is a major challenge, requiring a balance between latency, accuracy, and cost. Let's start by looking at the FPGA. Fundamentally, an FPGA is a semiconductor chip, much like a CPU or a GPU, but it is defined by three unique characteristics: the gate array, its programmability, and its field nature. Now, when we tackle tasks like model inference, we generally need to evaluate four key factors: performance, flexibility, cost, and power consumption. Unlike CPUs with weak acceleration power or GPUs which suffer from high power consumption, often exceeding 300 watts, FPGAs offer a unique sweet spot. They provide hardware level parallelism and energy efficiency without the prohibitive R&D cost of ASICs. This makes them an ideal platform for LLM acceleration. When we perform LLM inference, the process is divided into two distinct stages: prefill and decode. Existing research have already proven a key distinction between them. The prefill stage is primarily compute bound, and the decode stage is bandwidth bound. During the decode stage, the task is to generate output tokens one by one, based on the key value cache constructed during the prefill phase. Because each new token only needs to be calculated in relation to this cache, the actual computational load is relatively large. However, the challenge lies in the data movement. It requires a frequent, repetitive access to the key value cache. This leads us to a realization: whether we are looking at traditional model compression technology like quantization and pruning, or shifting to novel model architectures, or even employing the latest research method like fusion pipelining and data flow optimization. At their core, all these approaches are serving the same problem. They are all to optimize the hardware's memory utilization and bandwidth efficiency. With these contents in mind, I will now explain specifically how each of these optimization methods is implemented. Starting with model layer, the first major technique is specification. Essentially, this reduces the computational burden by pruning active parameters. We divided this into two types: structured and unstructured. Structured sparsity maintains regular patterns in the weight matrix. This is highly hardware friendly, as it specifies indexing and maximized parallel processing efficiency. Unstructured sparsity, while offering better comparison, creates irregular memory access patterns that can actually bottleneck performance. To address this, recent research have introduced the dynamic sparsity production. Instead of static pruning, this method products sparsity uh, patterns at runtime based on input feature, allowing the FPGA to skip fetching unnecessary weights entirely. The second is quantization. In inference, we rarely need full floating point precision. By lowering bit width, we can reduce memory complexity. This is where the FPGA shines. Its native Support for customer data type makes it the ideal platform for flex point composition. This directly relieves the bandwidth bottleneck by minimizing the volume of data moving between off-chip DRAM and on-chip SRAM. Recent studies even utilized mixed precision, dym- dynamically balanced speed and accuracy. Moving beyond the model layer, let's shift our focus to algorithm layer optimization. Here, the central keyword is bandwidth. For large language models, the primary bottlenecks is often not the computational power, but the memory bandwidth. The sheer volume of data transfer required between on-chip and off-chip memory can uh, severely limit inference speed. To solve this, researchers have introduced the smart strategies like column-aligned access. This method organizes data to match the physical structure of the DDR memory. By doing this, it avoids the time-waste process of frequently switching memory rows. This helps us get much better performance out of the existing hardware without changing the device itself. Another effective strategy found in recent studies is offloading. Since the high-speed memory inside the chip is very limited, we can move static data to external flash storage. Because the system only needs to look at this table once per step, keeping it outside is fine. Crucially, this frees up the valuable fast memory for data we use most often, such as model width and the growing key-value cache. This bond with focused method are essential for running larger model on FPGAs that have limited resources. Now, let's move from theory to hard data. In Table 1, we compare different hardware setups to back up our findings. We focus on speed, power, and a very important efficiency metric we call the tokens per GB. Our first key finding comes from compare different FPGA design. Take the work by Li et al. On the KV260 platform as an example. They managed to use 84% of the available bandwidth when running a 7 billion parameter llama model. That is already quite efficient, but the Hummingbird architecture took this even further, hitting a utilization rate of 94%. This 10% jump is a big deal. It allowed Hummingbird to run a larger 8 billion parameter model while keeping the speed amongst the uh, executely the theme. That clearly shows that squeezing even bit of bandwidth is a main key to fitting larger model on this small device. Our second finding appear when we compare FPGA against the edge GPUs. For instance, when we look at the tokens per GB metric, the data shows that FPGA solution can match or even beat similar GPUs. As table shows, while GPU have a lot of raw power, well-tuned FPGA offer better energy efficiency and perform just as well with the bandwidth they have. In short, this proves that for edge device, raw computing power isn't everything. The ability to maximize the bandwidth and manage memory well is what truly decided the limit of what these models can do. Looking forward, current research points to several exciting directions. First, memory and bandwidth. Since bandwidth controls performance, work is moving beyond simple fix. Researchers are now developing smarter ways to schedule data flow and manage memory. The goal is simple to squeeze more efficiency out of the available bandwidth and boost the tokens per GB metric. Second, we see a shift towards heterogeneity. This involves hardware evolution, such as FPGAs encrypted with high bandwidth memory, but it also means hybrid designs that combines FPGAs, CPUs, and GPUs into one system. By splitting tasks across these trips, we can use best strengths of each to maximize efficiency. Finally, there is AI plus EDA. Designed for FPGA has always been a slow process. FutureWork aims to use AI to automate complex steps, such as place and route. This would drastically speed up development, allow us to build and update LLM accelerators faster than ever. That's all my presentation. Thank you for your listening.